Interpreting correlation coefficient using a scatter plot is subjective, but there is actually a method we can use to get a precise measurement of the type and strength of our correlation. So as we looked at previously, we looked at how looking at a scatter plot and then trying to determine what the best fit line would be was kind of, again, subjective. It might be pretty obvious if it's positive or it's negative, but you're not really exactly sure how strong or weak that correlation coefficient is. So now what we're going to do is we're going to look at how do we actually calculate a correlation coefficient. The correlation coefficient is a measure of the strength and the direction of a linear relationship between our two variables. The symbol R is what we're going to use for our sample correlation. And this is going to be equal to the number of your ordered pairs, that is x1, y1, x2, y2, up to xn, yn. So for each ordered pair, this is one of your data points, you would have n number of those. And then this is going to be multiplied by the sum of your x values times their associated y values, minus the sum of your x values times the sum of your y values. And this is all going to be divided by the square root of n times the sum of your x's squared minus the sum of your x's squared. And then times, and then we're going to do the same thing for the y values. So it's going to be n times the sum of your y's squared minus the sum of your y's squared. And this is how we're going to calculate our correlation coefficient. Now, and again, an n in this case is our number of our ordered pairs. If we were doing this for population, it would be basically the same formula, except the symbol we're going to use would be a rho. So it's sort of like a P, but with a tail at the end. And of course, the only thing that really changes in the actual formula is instead of having a lowercase n representing the sample size of our ordered pairs, we would have capital N representing the population of ordered pairs. The range of this correlation coefficient is that it can be anywhere between -1 and 1. So our correlation coefficient can be anywhere from -1 up to 1 inclusive. This means that R can be equal to -1, R can be equal to 1, or it can be any value in between. The closer R is to 1, this represents a stronger positive correlation. The closer that R gets to -1, this would represent a stronger negative correlation. If R is equal to 1, this would be a perfect positive correlation or perfect positive linear correlation, meaning that as x changes, y changes by some exact amount every single time. So as x changes up by 1, y changes by some amount. As x goes up from 1 to 2, y changes by the same amount, meaning that I could then draw a line that perfectly goes through every single ordered pair. One of the misconceptions some people have is they think that by x and y being 1 to 1 with each other, it means that as x goes up by 1, if it's perfectly correlated, that y would also go up by 1. It doesn't mean that. It just means that as x goes up by some amount, y goes up exactly by the same amount each time. So again, if I go from x equals 1, 2, 3, 4, then y would go up by some equal amount each time. So it'd be like, let's say it goes up, as x goes up by 1, y goes up by 2.2. So it'd be, instead of 1, 2, 3, 4, it would be 2.2, 4.4, 6.6, 8.8. And then I could draw a line that perfectly goes through every single one of those data points. If R is equal to -1, this would mean that you have a perfect negative linear correlation. If R is close to 0, this would represent that either you have a weak correlation, or as it gets to a certain point, we just consider that there's no real correlation. As 1 changes, it doesn't really seem to have any relationship with the change in our explanatory variable. So now let's say that we created our scatter plots like we did in the last video. So in this case, we have dots kind of like this. If your dots appear to be going from the bottom left corner of the first quadrant up to the top right corner, and they're pretty close to this line, this would indicate that you have a positive correlation. And the closer that line is to representing the change in those dots, as closer they are to them and stuff like that, that means that it is a stronger correlation. If you have your scatter plot and you have in the first quadrant from the top left corner to the bottom right corner, this would represent a negative linear correlation, right? So as x increases, y is decreasing. And again, the strength is going to be how well does it describe those points. Here we have an example of a perfect positive correlation. So you'll notice that as x increases, y is increasing, meaning we have a positive correlation. And the way the dots are set up, I could have a line that goes through and touches every single dot, meaning that it is perfect positive linear correlation. Now again, I want to remind you though, in this example, they are going up 1 to 1, meaning as x goes up by 1, y is going up by 1. They do not have to have that exact relationship. It just means that as x increases by 1, y would go up by some amount. As x goes up by another 1, y would go up by the same amount, meaning that I could still draw a line through every point and it would look something like this. A strong positive correlation, you can see something like that here, where again, it's going from the bottom left corner of our first quadrant up to the top right corner. And then we could draw a line that describes this trend very well, but again, the points would not be perfectly on it, meaning that it's not a perfect positive linear correlation. Now you'll notice at the top, I actually did include the correlation value. So our R is equal to 0.92, which is, again, pretty close to 1, and it's positive, meaning we have a strong positive linear correlation. Here's a line to kind of show what this would look like. A weak positive correlation would look something kind of like this. So again, the points kind of have an upward trend as you go from the left to the right with your x. It does appear to kind of go from the bottom left corner up towards the top right corner. But if you look at our actual correlation coefficient, it's 0.459, meaning that it's not that close to 1. It's not really that close to 0 either. It's kind of in the middle, meaning, again, it's a positive value, so it's a positive correlation, but it is kind of in the middle, meaning it's a weak positive correlation. Now we're going to look at our negative correlations. So this is an example of a perfect negative correlation. And just like we talked about a perfect positive correlation, this example shows them changing in a 1-to-1 ratio. It doesn't have to be that as x changes by 1, y changes by 1. It's just that as x changes by 1, y changes by some amount every single time. And I could draw a line perfectly through it. So in this case, if we look at this, we have an R of -1. This is a perfect negative linear correlation. Now we have an example of a strong negative correlation, meaning again, you can see that this line that's on the graph represents this trend pretty well. The dots are pretty close to it, but it's not exactly touching every single point on the line when you cut it through. So if we look at the value at the top, we have an R of -0.93. Again, the negative tells us the direction. It's going from the top left corner to the bottom right corner. And the value, 0.93, is pretty close to 1, meaning that it is a strong negative correlation. Just like with the positive correlation, if you have values that are kind of in the middle, 0.4, 0.5, you might consider this a weak or a moderate correlation, depending on what thresholds you're looking for. So in this example, we have a negative correlation coefficient of R equals -0.498. So again, not really that close to -1, but also not that close to 0. So therefore, it does have some negative correlation, but it's not a very strong, precise correlation. As x changes, y does seem to change in some amount, but it really doesn't describe it that well. So looking at the line, you can see that it does have this negative trend, but again, there's a lot of distance between those points because, again, it's not that strong of a correlation. In this example, we have no correlation. So it is slightly negative. If you look at our R at the top, we have R equals -0.091. This means that it is pretty close to 0. You're generally not going to have R equals to 0, but in this case, it's actually pretty close. So if we were to try to draw a line, you'll notice that it is slightly negative, but otherwise it's almost a flat line. It really doesn't describe what's happening in a positive or negative way. And you'll notice from this that all the points are very spread out from it. Now, to use our correlation coefficient to make an inference about our population from our sample, we do have two requirements. The first is that our sample data pairs, that is our x and y's, have to be random. And then the second one is that x and y have a bivariate normal distribution. Now for this course, we're just going to assume that that's true, but based on other modeling types and things like that, this is something you might want to look into later. The last thing I want to talk about before we actually look at how do we do these calculations is to explain that correlation does not mean causation. So causation refers to a relationship between two variables where one directly influences or causes the other. That is, as X changes, it is causing Y to change. Correlation is just that there is a relationship, specifically a linear relationship. As X changes, Y also seems to change, but we're not necessarily saying that X is causing that change in Y. So causation implies that there's a causal link, meaning that, again, the change in one variable will change the other. This is extremely important to keep in mind because, again, we're calculating and modeling relationships. So while X and Y may have some relationship with each other, it might not be that X is causing the change in Y, but maybe something else that as X changes, Y is also changing in relation. Or it could just be that they're both related to something else. So now let's talk about how do we actually calculate this correlation coefficient. So normally what we're going to do is we're going to have a table set up with all of our data. You're going to have your X values, you're going to have your Y values. And then what we're going to do is we're going to calculate the sum of those X values. And then we're going to calculate the sum of our Y values. The next step is we're going to take every one of these X values and we're going to multiply it by its associated Y value. So this will be X times Y. And then we will get a bunch of values. We get one value for every single ordered pair. And then we will take the sum of our X's and Y's. Next, what we're going to do is we are going to take all of our X values and we're going to square them. We also, at the same time, or after we do the next step, we could also find these squares for our Y values. So we'll have one of these for every single data point we have as well. And then we will find what is the sum of our X squared and what is the sum of our Y squared. This will allow us to more easily calculate our correlation coefficient, which can actually be a pretty hefty calculation. So as a reminder, R is equal to N times the sum of X times Y minus the sum of X times the sum of Y. So from here, we get our sum of our X, Y. We already have that number. It's just going to be a number. We have our sum of our X. That's a number. We're going to multiply it by our sum of our Y. That's another number. And then this is divided by the square root of N times the sum of our X's squared. So this is this right here. And then this is going to be minus the sum of our X's squared, which is going to be this value right here. We're going to take the sum of our X's and then we're going to square it. And then we'll do the same thing for our Y values. We'll have N times the sum of Y's squared minus the sum of Y's squared. So right here, we've got the sum of Y squared. So we'll plug this in, and then we just take the sum of our Y's, square that, and then we should be able to plug all of this in and calculate our correlation coefficient. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.